Okay, we're starting applications of trigonometry, and we're going to do at least a couple of lessons on this, if not more if we have time. This first lesson, the key thing to recognize is that the diagrams are given. Okay, so we may still have to figure out what we're solving for in the diagram. It's possible that you're given a diagram that's missing a label and you have to add in a label, like you have to add in a side length or something like that. But for the most part, the diagrams are given. Moving forward in the next lesson, the difference will be the diagrams are not given and we will have to draw them and label them fully. And part of that is recognizing whether it is a right triangle question or a non-right triangle question, that kind of thing. Usually that's fairly straightforward. If it's a right triangle question, it's talking about a tree that's standing straight up or a building or something like that that is at a right angle. Okay. So we'll get started. So when you're not given the diagram, the trick to these really is drawing an appropriate diagram and fully labeling it. Once that's done, it's just a regular triangle trigonometry question. And you just ignore the fact that it came from an application and you solve it. And then at the end, you get some kind of answer that your calculator spits out. And then you interpret that answer. That's what problem solving or applications are all about. So let's take a look at this one. Oh, the neat thing about this, the applications in trigonometry are actually really cool if you think about how realistic they are. These are all things that people would actually have to do. Now, a lot of this is done by machines, and even the calculations will be done by machines, but people who work in machining industry, surveying things, measuring heights of things, I mean, they would do some of this calculation by hand for sure. Sometimes it's just easier than bothering to get a computer to do it. So and in some cases it's just interesting to notice how powerful the math is, how you can measure distances or heights of things very accurately with some simple tools and a couple of calculations. It really is amazing. So that's something to think about and reflect on as you're doing this. And a couple of the examples today, the first two, sort of have to do with machine work. So, creating parts for some kind of machine. And this is stuff that people actually do. This is stuff that people would actually sit down and calculate and would actually possibly use this kind of math for, or like I say, in some cases, there's a computer that's doing the math and there are robots that are drilling the holes, but it's still all been programmed and all been set up with an understanding of this math. So this really is real world math. It's not just math class math. This is good stuff. Okay, so example 1, 3 holes are to be located in a rectangular plate as shown. So hole A is drilled first, and then the table carrying the plate is moved horizontally so that hole C can be drilled, and then it is moved vertically so that hole B can be drilled. So imagine the plate that you're working on, and the table that the plate is sitting on can move around, again, maybe programmed by a computer, and every time it gets to its spot, the drill press comes down, drills a hole, and then the table moves again, programmed by the user. Okay? Determine the lengths of the horizontal and vertical movements. So we have to determine the length from A to C, and then from C to B, and that's what we will program into the computer. So even if the computer is the thing doing all of the work, we still have to tell it what to do. So we will have to do the calculations to figure out those lengths, and program that in, and then the machine, the computer, will do the rest of the work, right? So this is a right triangle, so that we're going to use right triangle trigonometry. We're going to use SOHCAHTOA because that's what we always have to do when it's right triangle trig. And as I said before, what's missing in this diagram is the what we're looking for, right? So I already said we're looking for this. And what happens when we are looking for a length that's unknown? We give it a variable. So I'm going to call that one x. And we're looking for this length. And so I'll just call that one y. And it doesn't matter that you use those variables. You can use whatever variables you want, a, b. Or we could call this little b, right? Because it's across from b. We could call this little a because it's across from a. You don't have to. I generally just use x and y. That's a pretty strong habit in mathematics that we use x. So I chose x and y, but obviously what variable you choose doesn't matter. All right, so let's get started. And I think we'll solve for x first, although before we even solve for x, we have a couple of other things that we can do that don't really matter. We're going to look at the values that we've been given. We know this length. Okay, and we know that angle. So we will use that angle. Of course, we could solve for angle B by subtracting from 180 because we have the other two angles. But there's no need to, and we don't want to confuse ourselves. So I think the best thing is just to use the angle that we're given. And so our first step in solving for a side or an angle in a right triangle using SOHCAHTOA is to label the side. So I'm going to do that. There's hypotenuse, there's opposite, and so finally this will be adjacent. Okay. And so now if I'm solving for x, now I can decide how I'm going to do that, which ratio I'm going to use, which of the three formulas I'm going to use. So I know the hypotenuse, and in this case I'm looking for adjacent. So which one is hypotenuse and adjacent? And that's ka, so cosine. So for x, we're going to use cos, and I can say cos theta, but I could also say cos A because that's angle A. It's already labeled. Okay, and then sub in. So adjacent is our unknown, that's our x. Now that I have it set up, I go back and I think about which type of question this is. What are the steps to solve it? Remember, there's three types. Your variables on top, your variables on bottom, or you're looking for the angle. And again, I will stress that whether the variable is on top or on bottom, those are different questions. In one case you multiply, in the other case you divide, and you just have to hammer that home because it's so easy to make the mistake to just kind of multiply every single time. So be careful of that. In this case, because x is on top, we are multiplying. I multiply both sides by 4.75, which will eliminate it on the right side, right? It'll divide out and then it'll be on the left side, but we usually just think about kind of bringing it over. And then pull out the calculator to get our actual answer. Okay, so 4.75. Oh, let's see if this calculator is in degrees or radians. This digital one is always a little bit tricky. Yeah, that looks right to me. So it's in degrees. So 3.74. Now the question doesn't say anywhere what to round to, but the length that's given is to 2 decimal places. So it would sort of follow and make sense that I would round this one to 2 decimal places as well. Okay. And we're not quite done yet because we're supposed to find 2 side lengths. So now we have programmed our computer and our machine to go from A to C to drill the second hole. And now we need to move from C to B to drill the third. So that's finding Y. And in this case, I still know the hypotenuse, but I'm looking for opposite. So that's going to be using sine ratio. I'm still going to use angle A, if you change the angle that you're working with, if for whatever reason you chose to calculate B, because like I said we can, and move over to B, then you have to relabel the sides, because then this isn't the opposite of B, right? Or sorry, it's not adjacent to B, I should say. It is opposite to B. So we have to be careful of that. So the best thing is, when you can, just don't change angles. Use the same angle that you were using. So we're going to continue using A, but sine is opposite over hypotenuse. So still using 38. Opposite is Y, and hypotenuse is again 4.75. And in this question, both of the actual calculations that we have to do work out the same. I still have unknown on top. The Y is on top, so 4.75, I move that over, and we end up multiplying. .75 sine 38, 2.92. Okay, so we found them both. That's what we were supposed to find. And like I say, you can imagine somebody actually doing this. You can imagine a machine that you can program lengths and tell it sort of directions to move, or maybe it just moves horizontally and vertically, and you may have to calculate those lengths in order to get it to move to the right spot to drill a hole, or you know, whatever the situation is. Okay, make a cut or something like that. Okay, this next one is another to me, very interesting application that you can imagine people actually doing. Drilling evenly spaced holes on a circular plate. So I can picture like a car tire, but the actual not the rubber tire part, but the rim that it sits on has holes, and those holes are evenly spaced, and the bolts go through those holes to, you know, get that tire secured to the car. And so when they make those, they have to have all of those calculations done, and whether there are 5 holes or 6 holes, you know, they're going to be evenly spaced in a circle. And that's just one application, but you can imagine any kind of, you know, sort of rim, like circular rim or circular plate or gear that has to be connected to another to a machine or another part or something like that, could have multiple holes, and you'd have to do the same thing like this. So this is, again, a really real world application. And so what we're going to do is we're going to calculate the distance between the centers of the holes, and this is a 16 centimeter diameter circle, and it has 9 holes. So this is one of the standard applications that we're going to see several times throughout this course. So it's one that you want to become familiar with. There will be some questions that could change, could be a little bit different every single time. And if you're given the diagram, then really, you know, the question could be about anything. If you're not given the diagram, then it'll probably be a somewhat familiar question. But this is one of the ones that we're going to see come up several times. So circular plate holes, drilling holes on a circular plate. Okay. So the diameter can change, the number of holes can change. So every question will be a little bit different, but the general idea will be familiar. And there's a couple of extra steps to this one that we need to consider. So that's what we're going to go through now. Tomorrow there will be another one like this, and we will have to, you know, draw the triangle. That you'll be given the circular plate, so you won't have to draw that part, but the rest of it, the actual triangle part, we will draw. Okay, so there's a few things that we want to think about. I'm going to get to the angle first, because that's probably the trickiest part to this. So we'll focus on that first, and then we'll talk about side lengths. So something to realize, there are 9 holes, And that is actually going to make 9 triangles. Okay? And I can turn them into triangles. I don't actually have to, but... So there I have 9 triangles. And these 9 triangles, because the holes are equally spaced, the triangles are all the same. So every triangle has this interior angle. And what we need to know is what those angles add up to. And so I'm going to pause for a minute and let you think about that, because this is something you might be able to think of. Here's a hint: when I put these angles together, they form a circle. So you want to think about how many degrees there are in a circle, and then we have to split that up into 9 even parts. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? We've got 9 triangles. So let me get rid of all that. And you may have already thought of this, and if you didn't, that's fine. If you did, that's great. But it's the same every time. Okay, so if I call this theta, then theta will be 360, which is the degrees in a circle, and in this case divided by 9, because there are 9 holes, which creates 9 triangles again, so that's all the way around the circle, right? And we'll just do that on the calculator. That works out to 40 degrees. So theta is 40 degrees. That interior angle. So that's always going to be one part of this question, right? We're always, it's going to work out the same, but every question that you do, you know, there'll be another question tomorrow that we'll do again, or in the next lesson, I should say. There'll probably be one in the review, and there'll probably be one on the test. And so every single time you will do the same kind of thing, where you'll take 360, divide by, and then divide by the number of holes on the plate, because that's how many triangles you would have, and that's how you can evenly split up that angle. Okay, so we have to find that angle. The next part is where it gives us the diameter. Now, diameter, you have to think about what that means. And diameter means what? Diameter means, sorry, I'm trying to bring out the ruler here, the distance all the way across a circle, right? So this is the center of the circle. Diameter is all the way across. So that is 16 centimeters. That's not directly useful to us, but how can we use that to talk about our triangle that we're actually trying to work with? Okay. Well, half the diameter is the radius, and that's going to be this length here. Half of 16 is 8, so 8 centimeters is that length. 8 centimeters will also be this length, and now we have some lengths and an angle in the triangle that we are working with. Okay, so it might give you the radius, like another question might give you the radius. Some questions might give you diameter. That's going to change in each case. This case, it gave us the diameter, and we had to do some thinking in applying that to this situation. Okay, so often when we're doing these, it can help to redraw our diagram, our triangle, outside of the bigger diagram. Sometimes we end up scribbling all over it because we're kind of thinking, and we're sort of, writing out diameters and all that kind of stuff. So sometimes we muddle up the diagram, or sometimes it's just useful to redraw the triangle without all of the extra junk. So I'm going to do that, and I'm just going to kind of sketch it. So I'm not even going to use a ruler. I'm just going to eyeball it. Okay. And here I have the 40, and I have 8, and I have 8. And then finally, we're missing one thing. This is an important part of diagrams, and if it's not already given in the diagram, then it is something you have to add. And if you're drawing your own diagram, your own triangle, or whatever diagram it is, you still absolutely have to add it. And that is our unknown. What are we actually solving for? I mean, that's going to help us know what to do next. So calculate the distance between the centers of the holes. So that's this distance, and we will call that x. So I could put the x here, or I could put it up there, but that's the distance that we're solving for, and in this triangle over here, it's x. So that's the thing about applications, is there's a lot of work that goes into them ahead of time before we actually start doing the math, the calculations that we've been working on, right? There's all kinds of drawing and labeling and thinking and all of that before we actually move back to using the methods that we've been learning and practicing over the previous few lessons, right? So now we can just look at this as a triangle. As I said before, we can just ignore the fact that this is an application, just look at it as a triangle, and just solve for x, right? If we've done all that early work, if we've done it well, then we've got our x, we've got our unknown labeled, we know what we're looking for, we hopefully know enough information to solve for it. If you don't have enough information to solve for it, then you got to go back and figure out what you're missing. Okay, generally speaking, in trigonometry, you need 3 pieces of information to solve for something else. And I don't want to get into this too much because this is not an example of this case, and I don't want to confuse anybody. But if you have 3 pieces of information, in this case we have 2 side lengths and an angle, so that's 3 things total. That means you can solve for something. That something might not be what you want directly, but it'll help you get there, right? So sometimes we have to do 2 steps, and we have seen that before. Sometimes we have to do 2 steps, but you can get there. It's a starting point. You have enough information to get started. If you only have 2 pieces of information, you don't have enough to do anything, okay? So we're going to ignore the fact that this came from an application. We're going to just look at this as a triangle. The first thing we think about, or the first thing we should think about, is it a right triangle or not? And in this case it's not, so we're using sine law or cosine law. And then, as we did in that lesson, we have to decide which one. So which one is this? Is it sine law or cosine law? And I hope that it sort of stands out. Again, the cases for cosine law often do stand out, and this is a straightforward cosine law because we can solve for x directly. And so I have 2 side lengths, and I have the angle between them, the contained angle. So that's cosine law, right? So cosine law looks like this: c squared equals a squared plus b squared minus 2ab cos c, where my c is x. So I like to, when I sub in for x, I like to take the square root of both sides as well, so I don't have to write it twice. So 8 squared plus 8 squared minus 2 times 8 times 8 times cos of the angle, which is 40. I'll take the square root of that. Whoops, what happened there? Okay. And then, depending on how you like to do things, you can do some of this work on its own, but if you have a good calculator, it's really easy to just sub in the whole thing, especially now that they have these calculators that look exactly like the question. Okay, and I've noticed the trick is, again, that when it's in a square root, I have to close the bracket. A lot of calculators are not picky about that. You don't have to close brackets at the end. It just assumes that's what you're doing. But when it's in a square root or a fraction or something like that, this calculator would give me an error. So I close that and I get 5.4. 5.47, we'll round that. Again, this question doesn't say, so don't get hung up on that. If we rounded it to 1 decimal place, that'd be fine. Round it to 2, that's fine. Just make sure you round correctly. Okay. And in the first one, I didn't do a therefore statement because there were 2 answers, and it's a little bit trickier doing that. In this one, again, I don't know. It's not the kind of word problem that screams therefore statement to me, But when in doubt, it's always a good idea to do that. Therefore, the distance between holes must be 5.47 centimeters. Okay, one more. And this one is less realistic in that nobody's going to stop during a hockey game or, you know, any other sport, soccer or something where you're shooting into a net and make calculations. So I don't know that anybody would actually do this, but what's actually interesting to me, and I've played sports my whole life and never thought about anything like this is a pretty realistic situation where you might be a few meters out and you're shooting at a net, and we're going to realize how small an angle you actually have to shoot within. And of course it's even smaller than that because you also have to probably shoot past the goalie or past the keeper. You have to maybe raise it to get it into a corner, an upper corner or something like that. So there's even other variables involved in actually scoring. But when we realize that when you're, you know, fairly far out from the net, and I think we'll do an example in the future with that involves soccer, and in soccer you take shots from even farther out. We'll see that it's amazing how small the angle is that you have to shoot within, and we don't really think about it like that, but it's kind of interesting. So this isn't so much a real world application where you're actually going to do this, but it's interesting. I would wonder if video games would do this kind of thing. I think they probably don't calculate angles quite that way, but they would be doing other kinds of high school math, absolutely, like quadratics and that kind of thing, when they're programming in you know a hockey video game, like how the puck actually moves. That would all be based on math, right? So there absolutely are applications in the real world applying to sports using high school math. There may be cases where people who analyze a game would do some of this sort of thing as well. They would do a little bit of math to see how fast the puck's moving, how fast balls are moving, that kind of thing. It may or may not involve trigonometry, but it would be other high school math and physics, right? So I don't know. It's interesting to me, and it really does. Again, like, I think it's important to highlight how these are real world applications and how math helps us with those. So let's read it. A hockey net is 1.8 meters wide. So first thing to notice is this is the hockey net, right? A player. So again, if you were not given this diagram, you would be drawing it and labeling it, but this one's given. So the only thing that is missing, as I said in the opening, is it's missing what we're solving for. So we are going to have to add that in. Okay. A player is 6 meters from one goal post. Again, if you're in the middle of the game, you wouldn't know that, so I don't know how you could even make this measurement. And then 6.7 meters from the other goal post, so they're off at an angle. Within what angle must she keep her shot in order to score a goal? So now we're thinking, like, where do we put that angle? And the player is obviously standing here, so that's the angle that we're looking for. That's our theta. And now that was straightforward, simple enough. Now we just have to decide again how we're going to solve this, right? We've got our triangle, we've got it labeled, we've got our unknown, we have 3 pieces of information so we can solve, and we have to decide what to do. Again, this is not a right triangle, so we're not using SOHCAHTOA, so we're either using sine law or cosine law. So which one is it? And again, I think it stands out because cosine law is usually easy to recognize. We're given 3 sides, that's cosine law. That's something you just need to know. Okay, there's no way to figure that out. You want to kind of memorize when you use cosine law and sine law, and everybody's going to be different, so you don't have to do it the way that I do it, but I do like to recognize cosine law. It just jumps out at me when it is cosine law, and those tricky examples of sine law can make you second guess yourself. So if you memorize the two cases of cosine law, which are this one, two sides and the angle between them, then it hands down that's cosine law every single time. And this is the other case, three sides looking for an angle, that's cosine law. And if it's not cosine law, then no matter what, you're using sine law, right? In this case, we're using cosine law. So cos C equals a squared plus b squared minus c squared over 2ab. And what's the trick to this? There's one key thing when we're doing the substitution that we have to think about. We can't just put the three lengths in wherever we want. It's the one across from the angle we're looking for. So in this case, we're looking for theta, this angle here, and across from that is the 1.8. That has to be C, right? That's the only trick, and then the rest of it doesn't matter. Doesn't matter which one's A and which one's B. Oops. Okay, so again, there's two ways that you can do this. Actually, I'm going to do that in green. So I'll show you the inside step, depending on how you like to do this. If you've got one of these fancy calculators, then you might be able to do all of this in one step. But if you don't, then you might just do the top first. So 6.0 squared plus 6.7 squared minus 1.8 squared. Now I'm going to get a bit of a, well, I'm going to get a fraction, but I'm going to get a decimal answer here, but that's fine, 77.65. Do not round that. Don't ever round until the final step. Okay, so I've got the top 2 times 6.0 times 6.7, 80.4, and then we're doing shift cos 77.65 divided by 80.4. Okay, and let's see what that gives us. That gives us 15, so that's going to be 15 degrees, but I'm not going to write that down just yet because I'm going to do a couple other things. If you don't have a two-line calculator and you're using a one-line calculator, then you might do it like this, 77.65 divided by 80.4, hit equals, okay, and you're going to get a decimal. Again, don't write that down and round it, because if you round it, then your final answer is going to be wrong. Just go shift cos at that point, and you probably don't even have to hit equals, but depending on how your calculator works, then it will spit out the answer, right? So again, you need to know how your calculator works. It's different depending on what it is. If you are doing it all in one step, it would look probably something like this, shift cos, and I'm going to use my fraction button because I have it, and it makes everything so much easier. So let me just make sure I didn't miss anything. Typing on the computer is sometimes a little tricky, but look at that. It looks exactly like it looks on the page. Hit equals, and in all three cases, I ended up with my answer of theta is 15 degrees. So that's pretty small. It's a pretty small angle that you have to shoot within, and the further back you are, the smaller the angle is. And of course, we all know that the further back you are, the harder it is to score, no matter what sport you're playing, right? So therefore, she must shoot within 15 degrees. Okay, and that's that. And again, when the diagram is given, that's usually quite a bit simpler. In some cases, if the diagram's given and fully labeled, it's almost like not an application question. It's almost just straightforward. Very often, the unknown, the thing you're solving for, won't be given, so you have to figure that out. If it's the height of the tree, well, then x is where the tree is, right? So you do have to still read the question and understand how the diagram relates to the question, but it's usually pretty straightforward. Okay. In some cases, you may have to label more. In this case, we had to label the side lengths and the angle and find the angle and the unknown. So in this case, this circular plate question, we had a lot to label. The first one, we only had to figure out where the unknowns, x and y, go, and same with this one, we just had to label the theta. So every question is going to be a little bit different, but generally speaking, the diagram will be given. So this is good practice to think about these diagrams and not just sort of ignore them, not just ignore the word problem, because as I said, moving forward starting in the next lesson, we're going to have to draw the diagrams ourselves, and that does add, some difficulty to these questions. Okay, so hopefully those three, fairly different examples. The two happen to be both cosine law, but that's no rule. You're going to use sine law a lot, but hopefully that gives you an idea of how applications with trigonometry, whether it's SOHCAHTOA or non-right triangles, how those applications work.